All right, let's decode the invisible world of sound. Every single noise you hear, whether it's a tiny whisper or a massive thunderclap, it's all built from the exact same blueprint. And once you see that blueprint, trust me, you are going to hear the world in a completely new way. Let's dive in.
It kind of feels like a trick question, doesn't it? One is so quiet you can barely hear it, and the other one can literally shake your house. But believe it or not, they share this fundamental, invisible secret about how they travel from their source all the way to your eardrums.
And there it is. They're both carried on these invisible waves of energy moving through the air. So that's going to be the main character of our story today, the sound wave.
Okay, so to really understand sound, we have to start with the wave itself. And it's not just something you see at the beach, it's a really basic way that energy gets around.
Now, this definition is so important. A wave is a disturbance that transfers energy. Just picture a duck, floating on a super calm pond. If you toss a pebble in, you see those ripples travel out. When a ripple gets to the duck just bobs up and down. The wave moved the energy, but it didn't actually push the water all the way across the pond. Sound works the exact same way, just with air instead of water.
But here's the thing, not all waves are created equal. Their shape, their very form, holds the secret code to the sound they create. So to crack this code, we've got to look at three key parts of a wave's anatomy. First up, we've got amplitude. So if you imagine that rest position is the perfectly flat, still surface of the water, the amplitude is just how high the wave peaks above that line or how low it dips below it.
This is a great way to think about it. Amplitude is directly connected to energy. If you give a rope a little lazy flick, you get a tiny wave with low amplitude. But if you really whip it with all you've got, you create this huge wave. So here's the takeaway. More energy equals bigger amplitude. Simple as that.
All right, next up is wavelength. This one's pretty straightforward. It's just the distance from the very top of one wave, we call that the crest, to the top of the one right next to it. You could also measure from the bottom of one trough to the bottom of the next. Same thing.
And you can see the difference so clearly here. That yellow wave, it has a really long wavelength. The crests are all spread out. But look at the green wave. Its crests are packed tightly together, so it's got a much shorter wavelength. It's the length of one full S shape.
And our last piece of the puzzle is frequency. So imagine you're just standing there, and these waves are passing you by. Frequency is just counting how many of those complete waves, from crest to crest, go past you in a certain amount of time, which is usually 1 second.
Let's go back to our rope. If you flick it up and down nice and slow, you're making a low-frequency wave. But if you start flicking it really, really fast, you're making a high-frequency wave. And we measure this speed in something called hertz, which really just means cycles per second. So a 2 hertz frequency means 2 full waves are passing you every single second.
Okay, we've got amplitude, we've got wavelength, and we've got frequency. We know the anatomy. But what does any of this have to do with the actual sounds that we hear? Well, this is where it all comes together.
The answer is absolutely everything. Those physical traits of the invisible wave are exactly what your brain translates into the world of sound. The shape of the wave is the sound.
So let's crack the code. We're going to directly translate those wave properties, amplitude and frequency, into the two main things you notice about any sound you hear.
This right here, this is the secret language of sound. The wave's amplitude, that becomes its loudness or its volume. So a bigger amplitude means a louder sound. And the wave's frequency, that becomes its pitch. A higher frequency gives you a higher pitched sound, like a flute, and a lower frequency gives you a low pitched sound, like a big bass drum. It's a direct one-to-one translation.
Let's look at this visually. On the left, you see that wave with a really high amplitude. Those peaks are tall. That's our thunderclap. It's carrying a ton of energy, so it's loud. Now look at the right. That green wave has its crests all bunched together. That means it has a high frequency, which our brain hears as a high-pitched sound, like a whistle. See? It's all right there in the shape of the wave.
Okay, now let's put this whole idea into motion with one of the coolest and most common examples of sound physics out there, the Doppler effect.
You know this sound instantly. An ambulance siren seems to get higher and higher as it comes toward you, and then the pitch drops right as it passes and speeds away. But here's the thing. The siren isn't actually changing its tune. What you're hearing is the sound waves themselves getting squished and then stretched out.
So here's how it breaks down.
As the ambulance is coming at you, it's basically catching up to its own sound waves, squishing them together, so more waves are hitting your ear every second. Your brain hears that higher frequency as a higher pitch. Then, the second it passes you, it starts racing away from the sound waves it's leaving behind, stretching them out. Now, fewer waves hit your ear per second, and your brain hears that lower frequency as a lower pitch. That's the whole Nina sound. That's the Doppler effect in action.
So, when you think about it, from the huge amount of energy in a thunderclap's amplitude to the shifting frequency of a passing siren, every single sound you hear is telling you a story. It's a story told through the physical shape and motion of these invisible waves. Now that you know this secret language, this language of amplitude and frequency, you kind of can't unhear it. You can hear the physics in music, in traffic, in conversation. So the next time you hear any sound, just ask yourself, what story is its wave telling me?